Okay, so we were talking about uh, lists, diction. Oh yeah, with dictionaries. Okay, so just remember, the notation is the syntax for defining these data structures is pretty I would say intuitive in the mathematical sense. So just a quick review. So the list we use square brackets. Okay, so for um so basically we have indices. All right, and the elements are changeable. Okay, and then if we look at the tuples, then the elements themselves you cannot really change. They're ordered, indexed, so you cannot really do append. In contrast to lists. Okay, and then we talk about sets. Then the elements are not indexed, and there's no ordering. The elements are changeable. So you can we have seen adding elements and removing elements. Uh, but for pop in a set, you would always return the uh, sort of like the first one. Okay, in the sense of hash table. Okay, so which is the way the memory are sort of registered for the data. So yeah, yeah. Let me try to make it a bit larger. So the thing here is that it's not so universal for Jupyter notebooks. Certain um, layout of the books are rather nice, but when there are pictures, then the layout may not be as good. So when you print them as files, then they make it a kind of not so universal. Well behaved printouts. Okay, so this one is a little bit small, so but let's for it's good for review. So when you are doing sets, we can do for loops. Basically, it's sort of intuitive in the sense that you just do for x in your set s. Okay, so that's instead of using the indices, we just sort of point to the elements. Okay, so that's the way that you write a for loop there. And okay, the dictionaries. Okay, the dictionaries they have indices, but they are keys. So it's also unordered. Okay, so dictionaries are unordered. The elements are changeable, but the indices are keys. So we are sort of like well, uh, when we talk about object-oriented programming, then you need to somehow set up your dictionary and then also just develop your class. So basically, it's gonna be a composition of certain data structure. Okay, so that's based on dictionaries. So basically, you have the keys that are these ones. So you can say them that they are the indices or they are the inputs in a sense. And then the data, they are the values. Okay, these are the values. Yeah, let me also circle that. All right. So basically, it's the necessary information that you want to include for, let's say, a car, right? And of course, if you can make more. So when you print the dictionary, then it will include every key corresponding every value. But then if you specify an index, let's say make, then it will return forward. If you specify my car with, so notice that the keys are strings. Okay, just so you do need the quotation, okay, for the index. So if you get year, then you would expect to return 1964, something like that. Okay. All right. So and of course, if you want to return all the keys, so in so it's so these indices are not really intuitive, and especially if you have a bunch of different keys, And if in case you forget, okay, how you define those indices, then you can use dot keys to return the key values. So that's some handy methods. And of course, to return the values, then you can just do dot values. All right. So and of course on your end you of course can play with the code cells, but here we prefer not to do that for the note taking purpose. All right, so now basically here starting from now we're gonna talk about the way that you measure the differences between data. Okay, so basically it's sort of like getting a little bit more uh biological discussion that we're gonna come up. So if you're looking at the basically the appearance of a bat, so its face looks similar to a mouse, but then if you look at the overall appearance, it appears pretty different. It's really up to how you sort of measure the differences. And in terms of your data, okay, so we're going to talk about more biological features a little bit later. But then when we talk about strings, let's say, so there are many, many different ways that you compare the differences. Okay, so let's say you have two strings, cats and dogs. So of course, they are the names, right? They're the kinds of animals. But then when you talk about the appearance of characters, right? So there are only one letter that's in common, and then you would say, okay, I can choose to compare how many different characters there are. That I would say coordinate by coordinate, right? Letter by letter, from the first to the last. But here you can see that, okay, they have the same length. So I can do the comparison, the leading character, then the next one, all the way up to the last of each of those. But then that method may not work well for S3 and S4 in the sense that they have a span and a spa. So now they don't have the same length, then you would say, okay, what's going to be the difference there? So the length is not the same, and you have one letter that's let's say for short, okay, for the string S4, right? So that's something you may notice. That's at the end. And then for S5 and S6, it's a little bit different, okay? Similar, but a little bit different in the sense that allowed and allowed, they have the leading letter being the difference. So now if you think about the component-wise, right? The coordinate-wise comparison, that would be a different thing, okay? So if you measure the entire words, so it's going to be the first letter that's different. So that can be one in terms of comparing the appearance of the string. But then if you do coordinate-wise, it's going to be what? It's going to be A and L different, L and O different, O and U different, and you have everything is different if you do coordinate-wise. So now, if you now think about S7 and S8, you have what? You have alien and cells. So if you think about component-wise comparison, we have 5 letters. In every coordinate, they're different. But now, if you look at the similarity, actually there is some similarity here. So you have A, L, and E. Okay, so if you want to add it from alien to cells, actually you do not need to replace all 5 letters. So you can say, okay, I eliminate I and N from S7, and then I append I add an S at the beginning and S at the end, right? So that's actually, if you think about editing, it's going to be an edit distance of 4. Right? So these are different ways that you measure the distances between strings. So it's sort of like a comparison of data. But it's really up to what kind of a measure that you would think that's reasonable. Okay. So just like we mentioned here, you have SPA and SPAN, then comparing similarity of strings, then you say, okay, I only need to change one. Okay, deleting the last one, that will give me S4. But if you think about component-wise comparison, it's a little bit different. Similarly for allowed and allowed, right? It's really up to the way that you consider or the way that you see fit. So indeed, there are many different ways that you define distances between strings. And then we're going to start with the first one, okay? The Hamming distance. One way is the character by character, the component-wise comparison is going to be what's called the Hamming distance. Up to the numbers, add up the numbers where they disagree. Okay. So indeed, for S1 and S2, you have the first 3 letters being different completely. The last one, they're the same. So that's the Hamming distance of 3. And if you want to code it, that's actually intuitive. So basically, you just start from the first, from the 0 index of one of the strings, and then it runs all the way down. Now here, let me think. So probably we don't really have to. So let's just keep the data on the board. So we don't really have to run the code to see what happens. So this is actually a really intuitive coding up, right? So we have S1 and S2 that the input strings. And then what do you see here? You see, okay, I'm getting the length of S1, and I run I for all the indices, right? So basically you have I from 0 all the way up to the length of S1 minus 1. So basically you're just saying I'm running through my string S1, and then I'm going to compare. If my ith index of S1 does not equal to ith index of S2, then I'm going to add my counter. Okay. So this is the intuitive implementation of the Hamming distance. And here you can expect there's going to be an issue because for S1 and S2, they're fine, right? So they have the length of 4 for both strings. But it becomes a problem for S3 and S4 because now you're running through, if you compare S3 and S4, you're running through a length of 4. And you're running the indices from 0 to 3. But then you don't have index 3 for SPA. So that's going to be an issue. So it's really up to when you try to make your implementation reasonable, you would want to think about possible bugs that the thing may pop up. So that's something. So this is exactly why make sure to run it on your end because S3 and S4 the Hamming distance that we implement in this way is gonna pop out an error. Right, and as we discussed, okay, S7 and S8, so they have the same length of 5. Then of course, you can component wise compare, and that's a difference of 5. Wait. ALI. Oh, the fourth element is the same because that's a 4. Hamming distance is a 4. All right. Make sense? So this is, yes? Yeah, well, that's sort of like the data pre-processing, right? So you want your data to fit your method, then you say, okay, I make the strings to have the same length. That's reasonable. Yeah, that's one way. But of course, if you are making the space for that SPA, then you would guarantee to Well, it's a possibility that the thing that you add is definitely going to disagree with the original data, or it's, yeah, uh, right. Yeah, let me fix my comment. So when you add a space, right, it's possible when that character does not agree with your original data, then that's fine. But then if they happen to agree, then you are in trouble.
Space so that they are the same length.
Right? Yeah. Well, the point here is that if you are, yeah, if you are sure that your character that you add is gonna be definitely different from the original ending character, then that's fine. So let's suppose they have yeah, they have a spa and a space, and you didn't know, and you just say I'll include a space for every string if the length is not enough, then that will give you an issue. So that's something you would need to worry about.
How would I
Now,
add spaces for every length string that isn't long enough? Then it's because the other one is longer, so then they're always going to differ.
Yeah, so let me put it down. So this is sort of like a false positive. So suppose your string is apple with a space, and then you are trying to get all the data to be the same length. But then you sort of predetermine that whenever there's not enough length, I add a space. So that's where the problem occurs.
Because you've made it so that the original data has a space.
Right.
Instead
So
of
so
adding space to continue data that is not.
right. But it's really up to you whether your rule that you implement would cause you some additional error or not, or gives you some trouble or not. Yeah, so basically you can include any random character at the end, but you would want to make it consistent, right?
Space was there at the end of apple, because if you're saying that I want my data to be as long as apple with a space, then apple with a space is the length. So I want whatever word I have to end in a space or to be the same length. End in the space.
I'm just bringing up a possibility that it may give you a false positive. So the data is, so let's say predetermined rule. So it's like yeah, it's like a priori rule or a posteriori rule. So it's gonna be determined before your data being processed or after you analyze the data, then give a rule. So that's different. So if you know that your data would not end with a space at all, then you just include a space. That's gonna be fine.
But even if I know my data is going to end in the space, then that's assuming I want my data to end in the space. So adding spaces and having a space match with a space shouldn't give me an error. It should be exactly what I want.
Yeah, well, if you know some of the data may end in space, then these two strings will give you identical distance.
But the space is being represented by a character, so apple without a space is not the same as apple with the space. So I would have to add a space to second apple in order to make them be the same. So I would still have a hand with a 61.
That's gonna be a 0 once you process it. That's the problem.
Is space not considered a character?
A space is considered as a character.
So then.
Oh, it will give you a Hamming distance of 0. Oh,
because adding the character space is my Hamming distance 1.
Oh, then you would need to define that, right? So yeah, then you would need to modify your code. That's the point. So
the character by character in the string. So why would I have to modify it?
okay, let's think about the logic. Yeah, the are we do we see the problem? So let's be on the same page for the discussion. So yeah, this is an important way to think about the code. So here the logic is okay. If the strings do not have the same length, we can try doing this kind of data pre-processing to make them the same length so that the code could run through, right? And then the method we propose disregard of the data is that we add a space at the end. And now if you just run the code by the way it's written, it's saying I have the two strings and then I do component-wise comparison. So let's suppose here, unfortunately, we have the data of Apple with a space and Apple with no space. So they should give you a difference. But then once you do the pre-processing, you will have the same length with Apple and following it with a space for both strings. Then running this code will give you a Hamming distance of 0. So this is a false positive, telling you they are essentially not the same, but you identify them to be the same.
So you're saying you have to change the code so that added spaces are
considered as a distance. Yes, that's some modification that you have to do to adjust to your situation. But in terms of Hamming distance, it's kind of like super basic. You just component-wise compare. So which is what we are seeing right now.
So if I do add space to spa and then rerun the same code, it will still give me an error, correct?
If you directly add a space to spa, then it will not give you an error. Interesting. Let me see. Okay.
So I added space and when I say S3 equals S4. It's not
Don't change that. That's S1 S. Don't change the data here. Just change the input. That's the
so it should not say.
Well, if your code runs through, then don't try to change the thing within the definition of the function. So let me where are we? Yeah, if your function is like this, right? If you have S1 and S2, then make sure not to change the variables, because otherwise it's going to be undefined. So if you have the space here, and then this kind of Cuban sum when I do not have my mouse, and then I have I need to highlight this line, and let's see. So that should give you an error, because now you have valid indices. But then if you remove the space, that will give you an error, because okay, we don't have index 3 over there, okay, for S4. So that's the thing that you should expect. So yeah, so basically the point we were touching is that, okay, of course you are free to do data pre-processing the way that you want, but then just make sure that it will not bring you some additional issue. So the potential issue we just mentioned is that your rule that you implement for the data processing somehow need to be data aware. So if there are different characters, let's say there are spaces, then you may not to add space at the end. So let's say use some uncommon character that's not in your data that you are sure of. So let's add a pound, but just to make sure that the calculation is not giving you some like false positive. Yes.
To see what would happen to change, like from doing a strictly increasing order, like choosing, S2 and then S3 and S1 and then S3. I did like choose S4 and then S1 for my input. And it gave me And the answer, which I thought was to be 5.
S4 and S1.
Work.
S4 and comma S1 S1 and S1 is fine. Yeah, that's a very good point, and we can test that. S4 and S1 is actually not problematic because you actually run through SPA and done. So you didn't really consider the index 3 for S1, which is what? Which is S, right? Cats. So yeah. Just be aware of what kind of code that you're getting through. That's all. So that's a problem. So yeah, for different lenses, then what do you do? So that's something you need to worry about. Let's give a bug. Okay, we can leave it like that. So far so good. So we can let's move on. Okay, so here just pre-processing. Make avoid like false positive. Okay, positive. All right. So this is this is a nice comment that's that may be utilized in the future. So basically, why do people do Ham distance? Because actually it's originated from binary strings. For binary strings, you don't really have a lot of information. It's just going to be a string of zeros and ones, just like the what's that called? Binary digits, right? So essentially, of course, when they have the different lenses, they're different, but how different are they? So that's the reason why people are just doing just component-wise comparison. So, and the thing here is that when people are doing error detecting or error correction of code in the computers currently, as long as you are not dealing with what's that word? So the traditional computer is 0, 1. Quantum computers are not doing this the same computational logic. So that would be pretty different. But in terms of traditional computer with the binary memories, then the Hamming distance is more of a kind of dominant distance measure. Especially when you have binary strings and you don't really know what actually is behind the data, right?
Professor,
Yes.
help me understand the question she asked.
Oh, sure. Just now, let's get back to. Let's go back to that S4 and S1. So yes, let me copy that line. So
C. But then it doesn't take into account the fact that it's causing 3 characters and counts as a whole. So nothing gets compared to the S because you're done through like S4.
But S2 square brackets I is indexing the index, not the value within that. So
Yes,
yeah,
but that means that once you go through S3, you stop comparing, even if the one following the not equals 2 has more characters.
but then it should be 1. Why 3? Why you get answer 3 and not 1?
Would you do S4 to S1 or S4 to S3?
S4 to S3.
Because S is different from C, B is different from A, and A is different from C.
So S1 is taking the character and not the index position.
The index position is where the character is.
Yeah. Can you please solve?
Oh, yeah, I was kind of trying to see if the explanation between your discussion would help. But yeah, well, the idea here is indeed go back to the algorithm and carefully analyze, right? So we are looking at so it's a little bit confusing in the sense that okay, the input here is S4 and S1, right? So S4 is in the place of this.
Yeah.
So you are looking at the length of S4, which is 3. So that's everything is pretty much fine up to this point. So I goes from 0 to 3, right? So now you're comparing. Remember, S1 is your input of. Just look at your function call. It's S4 at the zeroth index, which is S. Okay. And then S2 is that the input at S2 here is your S1, which is at C. So now that the counter would have to add 1.
So S4 of 0th position, it
Yes.
will take the letter and not the position.
Take the letter.
Okay.
Take the letter. Yeah. So it's the string at that index location. That's my character S comparing to my character C. And then you take the index 1. So indeed, the whenever there's a difference, that will accumulate. Yeah.
And if I only want to see if the length, now that it's the smaller thing, but if the length of the two variables or the lists are different, and I want to know how much are they like, what's the difference value between two lists? How do I do that?
So
I do not want what the different strings are. I only want the number of difference. Like if one thing has 5 letters and the other one is 2, 2-letter word, and so the answer I need is 3. The difference between first and second is 3 letters.
Oh, if you only compare the lengths, then what you can do is use the difference of lengths and then take the absolute value. So that's a reasonable measure. So just use the length of the first input minus the length of the second input to get a difference, and then to get the absolute value. Yeah. But then that will cause you additional issues, right? So that's one option of the difference, but it just it may not be very good. So yeah, we can continue with the screen. So now the way now this is one more comment. Okay, so we have S4 and S1, right? So it will be an issue if you are comparing SPAR with SPAM. So SPAR and SPAM, they appear to have no difference, but in fact they do have difference, because SPAR as S1 is actually going to run through the first 3 and done. No SPAR, no space, just with no space. But yeah, just think about possible issues that you may have for your code. So yeah, this is a really intuitive way that you consider things, but it may not be perfect. So of course, later we're going to talk about the one that's also considering the added distance. Okay. Yeah, so indeed, so for computer error coding, error correction algorithms, there are sufficient powerful ones. So that's the method that they use to somehow to get these CDs and DVDs run smoothly. So that's one correction that you may get for like blurry Mona Lisa. Okay, so that's just by doing 0-1 binary error correction as an example. Then so now for viruses and RNA, it's a little bit different of a story. Okay, because if you now think about RNA, it's not as stable as DNA, so it's like one string of instead of two strings. So two strings is more stable. So the way the RNA perform in, let's say, viruses is that, okay, it's trying to replicate itself, but then it will also want to mutate so that it sort of adapt to environment. And then you would say it will try to copy its generic data, but then it also wants to change, right? But then the change is not really component-wise. Sometimes it may drop certain parts. Sometimes it will add additional. Sometimes there will be errors in terms of copying. So that's a more of like a motivation for the added distance. Okay, so yeah, well, here one observation is that indeed for RNA reprocessing or reproducing themselves, they also have sort of proofreading mechanism. So somehow they would want to mutate, okay, be able to reproduce and be able to evolve, but also at the same time they want to preserve certain genome within the reproduction, so which will not be self-destroying. Okay, so that's something interesting within their encoding. And well, if you think about cancer, indeed there will be a lot of mutations. So what does it do in terms of mutations? There are a few things that could happen. Okay, so let's say for a normal sequence, we have CTAG. A possible mutation is that, okay, I insert a G. So now if you think about the Hamming distance is going to be really a significant change. However, just in terms of the mutation, you just add a G inside the original string. Or it's possible that you can delete, let's say, the piece A there, so it will become CTG, which is also this one removal, right? Then this is another case that you need to think about when you sort of try to code this added distance. And it's also possible that, okay, when it's reproducing itself, it malfunctions, so it duplicates certain parts for unnecessary circumstances, like here repeated CT. It's possible to do that. So then one thing that's important is to somehow categorize this kind of added distance. Oh, here also, this is if it's a CTAG, it's sort of inverted a TA with AT. It's also sort of one change, but then it significantly changes the original data. So why is it helpful? So before, so this is a discussion we can quickly go through. So basically, scientific theory that we have that the lives are sort of evolved from a single origin and all the way branching into different kinds of animal species, but then you would have to think about an essential way that you can analyze, right? So basically, depending on whether there's a spine or not, depending on whether animals will do breastfeed or not, and then there will be different kinds of categories of animals, and then you would want to trace back to the origin. So that's a theory depending on the appearance and depending on the behavior of species. But then when we get into DNA, it's a little bit different. Okay, so indeed, so for the appearances, we have mammals, we have reptiles, we have fishes. Okay, and of course, when we go even earlier, then there's not even spines. Okay, this is really the lower level species. One thing sort of interesting is that, okay, we have apes, we have men, we have if you're looking at the old like branchings of the species, we have man, We have bats here. Okay. So we have apes here and gorilla, in a sense. So one thing interesting is that the theory actually changes a lot before and after the analysis of DNA sequences. Okay. So here, so this is actually saying what this is actually saying. Basically, the chimps and gorilla, they seem to have like a common ancestor. The branch. So basically, the branching is they separate human and gorilla and chimps first, and then gorilla and chimps. So it's sort of like the branching is earlier for human to separate from those species in terms of the analysis of the appearance and the way that they live. But DNA sequencing will give you a little bit different information. Okay, so if we are doing the DNA sequencing based analysis, actually we have a little bit different of a tree. So basically, the way that they do is they somehow trace the strings of DNAs and sort of analyze the added distance. Okay, so basically, the theory is the following. So there will be mutations throughout the evolution, but basically the mutation would, because we have DNAs that are two strings, it's much more stable. So it's sort of saying, okay, you have stable mutations with a certain fixed number or a relatively stable period of time. Because let's say a few thousand years or 100,000 years. So basically, if the rate is assumed to be stable, then we will be able to sort of trace the added distances and compare. So which species are close and which species are further away, and then the more changes there are, then you would sort of get the hypothesis that the mutation separated them at an earlier time point. So now, based on this kind of I would say assumption or some scientific assumption, I would say hypothesis that we actually find that human and chimps, they separate at a later time point than the separation from gorilla. So which is theoretically and scientifically interesting, that basically human and chimps are closer compared to gorilla, which is a little bit different from the traditional analysis of species. Okay, so that gives you an idea of why we care about the added distance. Okay, so basically, when we have data, we want to see how many changes there are that we need to change from one to another. So this is sort of like the motivation of why we care. So so that's leading up to our more flexible distance of measuring. Instead of the Hamming distance of component-wise comparison, we're just doing, okay, calculating to change from one string to another, how many changes do we need in minimum? Okay, so this is a procedure that we need to be careful about the coding. So far about the motivation, is it clear now? It's actually just we want to calculate how many operations we need to change from one to another. So what are the changes possible? So it could be a substitution. Let's say there's a maps and by mistake it gets to mops, right? So that's one change. We just see from spam to spar, we deleted m at the end. For loud to allowed, we included an a at up front, right? So it could be insertion, it could be deletion, it could be substitution. And we discussed the alien and the cells earlier. So in fact, A, L, and E, they are already there. So the Hamming distance is a 4. And so let's see. Insert S, delete I. Oh, here. So we don't really need a for, because here we can substitute for the last step to substitute N for an S. So if you allow substitution, then you don't really need to delete N and add S. So that's considered as one operation. So that means what? That means the added distance is actually a 3. Okay. So just keep in mind that we have A, L, and E, right? So we add an S up front, so and we get rid of that I there, then I have cell with N ending, and then I replace N with an S. So that's actually 3 operations if we allow substitution there. All right. Yeah, so basically now in terms of the coding, we just need to put them together. So that actually requires a little bit of design, which is the recursion that we have seen from before. Okay. So added distance. So the way that so the distance on strings that use the above 3 types of mutations is called the Levenshtein distance, and it's one of the several types of added distances, which includes Hamming distance. And here, basically, if you're computing the minimum added distance between strings with A of length M, B of length N, then essentially you are sort of trying to see if any of the operations above can reduce your distance that follows. Okay, so here's the idea. If they do not have any length, so if one of them is just empty, okay, so if I or J is empty as a string, then of course you have wait. Okay, so let's be careful. So A has length M, B has length N, and we define a lev sub AB of ij to be the added distance between the first I characters of A and the first J characters of B. So if any of them is 0, okay, so if I or J is 0, then of course the other one that's remaining, that will give you the difference. So you have a string of I and comparing with the 0, okay, so that's gonna give you an I. If you have a J, if you have I to be 0 and J is something positive, and then of course you're comparing with the empty string to a string of length J, then that's gonna, of course, you would need to add it J times to get to that added distance. So which is why here, that's the base case. Whenever there's a 0, then you would just return the maximum of I and J. Okay, so just returning the other one. So that's sort of like the base case that you would utilize for recursion. Okay. But then, so now, if here you're just saying, okay, if the first characters, they are different, it can be several cases. Okay. So it's possible that the first one, let's remove excuse me, for A, the first I components, you remove the first letter, and then they will have more similarity for B, for the J components of B. And then you would just direct to a recursion of a sort of like a subproblem, okay, adding a 1. And then it's possible that, okay, if I can remove an element in the string of B, and then that will give you more similarity back to A. Okay, so that's the one addition that's included right here. And finally, there's a case that okay, so those characters are indeed different. Then you would just consider that as one mismatch, and that you would have to do this substitution in a sense, and then you would get the remainder problem of just completely discarding those different characters. Okay, so that's reducing to I minus 1 and j minus 1. So basically now here, of course, we have three different strategy of doing this kind of calculation, but you are trying to look for the minimum, so you take the minimum of those. Okay. So yeah, let's just make sure that yeah, so let's go back to our notes to put down some comments, because indeed we have three ways to play with the data. So we have substitution, insertion, and deletion. Okay, let's remember that. Substitution and insertion and deletion. So basically, it's always from the left to right. Okay, what you would have to do. So these two are about addition and deletion. And this one is for substitution. You are sure that AI and BJ are different. All right. And this is indeed a recursion that you are trying to write up. All right. So now let's keep that up front, and then we just look at the design of the code. So basically, the top one is the base case. Okay, either I or j is 0. Okay, so we're just once again we're looking at the first component of A and the first I component of A and the first j component of B. So it's just the indexing that we are playing with. The original data A and B are the same. They're just intact. Okay. So the base case, whenever your inputs S or T has 0 lenses, then we return the maximum. Okay, so that's this part, the base case. And then, so if they have the same character that they start with, then that tells you you do not need to do edits for the leading. So you directly jump to just removing the first characters, okay, for S and T. So this is the recursion over there. Okay. If they have the same starting character. So that's sort of like an intuition behind the loops that you're gonna do. Okay, but then let's see. We would need to do the use it or lose it strategy, just like what we have seen in subset sum. So because here it's possible that okay, I add an element that will give you the same thing, or I remove an element. So just from the original data. Okay, so it could be addition, it could be removal. So here, this is saying, okay, I either use I need to use a substitution to make the match. So this one is from substitution. So I have to do the change and then refer to the remainder of the data. So that's still added distance between S starting from 1 and J starting T starting from 1. Or I try deleting the first. Okay. So now deleting the first is actually from S. And then if you are trying to insert a character from in front of the S, then that's actually saying, okay, I'm sort of removing the first of T. So that's sort of equivalent. So just think about what's going on right here. So this is deleting, let's say this is my string S. This is my T. So I want to delete this one. Okay, so that's doing S removing the entry 0. Okay, so that's the idea there. But then it's possible that I want to insert. Okay, so I want to insert B, and I know there's a B up front. Okay, so insert here is the same as string word. It's the same as just not insert but remove that B there. Because anyway, one operation that you do, you need to increment that 1. So that 1 is right here. Okay, so that 1 is right here. So this one is right here. Just be aware of why we are doing this. All right, and then basically we sort of could handle these 3 different strategies. Okay, substitution. Wait, yeah, this is the problem of the printout. So the reason why we have this kind of small fonts is that it doesn't display really well. Okay, so yeah, we can go back to the code. So I think we don't really have a lot beyond this point. So let's look at the code. So the 3 strategies are here. So base case, of course, when there's a 0 length, then the other one gives you the added distance, and the recursion with 3. So substitution, we are sure that the first one for S and T, they're different. Okay, and then you are thinking about the possibility of adding just removing the first character of of S, or removing the first of T. Okay, so that's the code. So now let's compute. So here we still use alien and cells. Okay, so that's a 3. Okay, so that's the set. Well, that's the intuition that we began earlier. So you add S at the upfront for alien, and then you remove I and then replace N. Okay, so that's that 3 there. And let's try allowed and loud. So you would expect what? So allowed and loud, if you are doing Hamming, you will get a lot of errors. But here you're just removing A, right? And it also can handle different lenses. Let's say loud and allowed. So it's the same thing. Okay. So basically, the 3 strategies, if you look at these, they are symmetric in the sense that, okay, if you swap S and T, essentially the steps will not change essentially, right? So when you think about the interchange of S and T, then lens T, lens S, so the OR statement is doing the same thing. The length of T and S to take the maximum is the same thing. Comparing the first elements, that's the same thing. The added distance of the subcase of T and S, that's the same thing from before. Just sort of like assume your function is symmetric for strings that have lower lengths, then sort of through an induction argument, okay, if the subcases are symmetric, then building upon those, the thing itself is symmetric. And then here S and T are changed, that thing is still the same. But then if you change this to T, change this to S, then those two lines are swapped. Okay, so that's sort of like the logic of symmetry that you can think about. And of course, here in the code, we have what? We have substitution, deletion, and the insertion right there. So that's sort of like helping you to get an intuitive idea of what you are coding on. Okay, so of course, in the future, if you are coding your own ideas, that you may want to use some intuitive variables to help you memorize, and also include comments if necessary. All right, so that's let me see what else are below. Oh, right. So I already answered one of the reflection questions. So is this symmetric? So think about whether the added distance between the string S and T equals to the added distance between T and S. So is this non-negative? What do you think? Clearly, right? So everything builds up on the base case, but base case is always a maximum between 0 and some positive number. It's of course non-negative. So what do you think? Does it satisfy triangle inequality? So actually, it should, but of course, you do need a little bit of an argument. So basically, the logic is that, okay, the added distance tells you what? It tells you the minimum characters that you would have to change, okay, to get from one to another. So the distance between X and Y plus the distance between Y and Z, you would want it to be the upper bound of the distance between X and Z, right? And which is true because this is saying this is the number of changes from X to Y. And this is the number of changes from Y to Z. Right, so if I do the right-hand side, add it up, that will make sure that I can change from X to Y, then from Y to Z. And the left-hand side is actually possibly a smaller number because that's the smallest possible changes from X to Z. So indeed, this is actually a metric in a sense. Okay, so if you think about this properties, it's symmetric, it's non-negative, and it's satisfies triangle inequality. Right. So yeah, well, the lecture here probably is not for you to come up with your own design of this, but think about the way that you can systematically construct this kind of definition so that it fits for different sides of data, right? So that's good. Okay, so now let's jump into the live coding session for this class. I should firstly open it up. Yeah, here. So yeah, we still have some time before the class ends, so you guys can play with the stuff. And let me share the screen. So the first one, if you would like some hints, I would say the Colab actually gives you certain hints. But basically, the idea is that okay, you have intervals which are sort of really short lists, right? Two elements of list of two elements. Then you would want basically run through all these intervals to see if your number that you input is between the two values of your intervals. So of course, to make it a little bit more sophisticated, you want to make sure that for every sublist that the data, the left-hand side is less than equal to the right-hand side, but that's not necessary as long as your data are fine. Okay, so just make sure to count through how many values there are for your value to be between your uh, uh, element zero of the list, sublist, and the element one of the sublist. And indeed, there are many different ways to write a for loop. So just now, it suggests for the interval within intervals, just like accessing elements within the list. But here we can also just do the indices. If you're done with exercise 1, make sure to play with exercise 2. This is a very interesting one. So you know that a dictionary has different keys, right? But here we specify, let's say for 11 keys, then it's going to be key 1 all the way up to key 11. So you may need to enclose those key and value correspondences in a loop. Okay. So every time include let's say key n corresponding to value here. This is m. Oh yes, this is key 1 corresponding to n, key 2 corresponding to n minus 1, key I corresponding to n minus I. So these are can be established through a loop. All right, it's almost time, so we can continue on Monday for the session. But basically, what I'm writing here is the homework that you did, which is all permutations. But basically, what I'm writing here is that okay, for the beginning element, I'm gonna remove it and then do the rest of the permutations. But then for the current element that's different from the previous, I can continue with the permutations. But if they're the same, then I can drop it because let's say 113, you remove the first one due to permutation. And then for the middle one, then you don't really need to repeat the process because removing that one there is going to result to the same thing as 1-3. Okay, so just something you can think about to make your code run a little bit more efficiently. Yeah. And we can continue on Monday.
Okay.
Yes.
Right space, this is problem set the reads to be may. Is that true?
Yeah, well, there are things that are so the first few questions you are able to solve right now, but there are questions that are a little bit more involved for latter part of the course, which is about output-oriented problems that you need a little bit more time to need to cover for a few weeks after the break. So that's actually the reason why we make it due by the end of the semester.
Okay.
But yeah, you can finish as soon as you know how to solve those problems.
Yeah.
And then we will also make a few homeworks for materials that are after the break. So
Okay.
yeah.
Alrighty. I was just curious about that. Thank you.
Beyond everything from lecture 6 now.
Yeah, well, the official answer is yes. But the emphasis will be a little bit more on the prior material.